Hello students, welcome to lecture 14 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today we will look into the applications of SPPs, that is surface plasmon polaritons. So here is the lecture outline. So we will continue where we left in the last lecture. So we will start with generation of SPPs. There are two methods, prism coupling and grating coupling. Then we will look for some applications of SPPs in sub-wavelength optics. We will look into SPP waveguides like metal wire SPP waveguide, metal groove waveguide and double strip waveguide. These are the different applications. We will also look into plasmonic laser, electro-optic modulator, plasmonic detector and application of SPP in sensing applications such as refractive index sensors. So let us look into the generation of SPP. So surface plasmon polaritons on a flat metal dielectric interface cannot be excited. So if you remember from the last lecture that we have seen this particular dispersion relation, right? And what was the reason that we described that this is the light line for air, okay, and this is the light line for silica. And here is the look at the solid curves, not the dashed ones. So if you look into this gray color solid curve, that is basically the dispersion relation of surface plasmon in metal air interface, okay, and the black one shows the surface plasmon's dispersion relation in metal silica interface. So this black line and this black line, so this is for silica light line and this is the surface plasmon dispersion. So when I say light line, we basically talk about photons, and here we are converting things from photons to plasmons, right. So there has to be a case where there is a momentum match. Now we have seen that in most of the cases beta, that is the propagation constant of surface plasmon polaritons, they are larger than the k, that is the wave vector of light in dielectric medium. It can be air or silica. In both cases, for air you see this is the photons and this is the dispersion relation of plasmon. So it means the momentum at a particular frequency, you can see the momentum of the plasmon is higher than that of photons, okay. So because of this momentum mismatch, you are not able to transfer energy from photons to plasmons. So if you try to use some kind of light impinging on a interface like metal dielectric interface, in that case the amount of momentum that you will be able to transfer is basically kx. X was the direction of propagation, if you remember from the previous lecture. Then kx sin theta would be the component of the k is the actual wave vector. So kx is that component, x component, that can be calculated as k sin theta, right. Now at any angle, what can be the maximum value of sin theta? That can be 1, right. At any case you will see that these are basically smaller than the SPP propagation constant beta, even at the grazing incidence. So that is the case. So in every possible scenario, if you simply take a metal dielectric interface and shine light on it, even at very tilted angle of incidence, you will not be able to excite surface plasmons. It means phase matching has to be somehow achieved, and for that you have to use a 3-layer system. That means you have to insert a metal film sandwiched between two insulator of different dielectric constant. So that is the only possible way to excite surface plasmons, as we will be seeing here. Not only, that is one of the most popular one, we will see another method also possible, okay. So in this particular case there are two configurations possible, one is called Kretschmann and another is Otto configuration. So this method is also known as prism coupling, okay. So for simplicity we will take one of the insulators to be air, okay. So a beam will be reflected at an interface between the insulator of higher dielectric constant, which is in the form of a prism. So this dark slab here is basically metal. On the top it is air, and below the metal you have a glass prism. So, it is a higher dielectric constant. Okay. That is why it is called prism coupling, because you are using this prism to excite surface plus bonds. Now, this particular configuration is called Kretschmann configuration, and this is the most common configuration, and in this case you actually have a thin metal film evaporated on top of a glass prism. So, there is nothing between the glass prism and the metallic film. Okay. The film is actually deposited on top of the glass prism. Now, if you look into the photons, these are photons that are entering into the glass prism. Okay. So, when the angle of incidence is greater than the critical angle of this interface, you will see that there is total internal reflection. Okay. And if you remember total internal reflection, okay, there is some kind of evanescent wave also generated. Now, when there is total internal reflection happening, okay, some part can actually tunnel through this thin metallic film, and it can excite surface plus bond polaritons on the metal air interface. Okay. So, it will be able to do that on the top side, okay, that is on the air side. Now, the metal will have a in plane momentum which is given as kx. You can write it as k square root of epsilon sin theta, okay, and this will be sufficient to excite SPPs only at the interface between the metal and the lower dielectric constant, that is air in this particular case. You can see from this dispersion relation. So, you can actually think of dispersion relation as the main lookup thing in plasmonic case. So, this is the light line in air and this is in prism. Okay. So, prism is made of glass. So, glass, you know, the refractive index, it can be 1.55 roughly. So, what is happening? So, you see that if you take this particular, if you are using this particular line for the incoming wave, okay, or incoming photons, then you will see that there is a possibility that you can actually have plasmons which are having lower energy, or you can say lower momentum, okay, not energy, we will say in terms of momentum here, lower momentum or k vector as corresponding to this one for a given frequency. Okay. So, by changing the angle of incidence, you will be able to match the kx component with the beta of the surface plasmon, and this is how you will be able to match them. So, which one is possible? Metal air interface is possible. What about metal prism interface? Because there is another metal dielectric interface, na, this one. There in no way you are able to match the momentum of the photon to this one. So, exciting plasmons on metal prism interface is not possible, okay, as simple as that. Fine. Now, as I mentioned, so this way only SPPs with propagation constant beta that falls within the light lines of this air and prism, this one can only be excited. Fine. So, also note that the phase matching to SPPs, this one cannot be achieved. So, you will be not in a position to excite surface plasmons on metal prism interface. Fine. So, this particular prism coupling scheme is also known as attenuated total internal reflection, and it involves tunneling of fields, okay, of the excitation beam to the metal air interface where SPP excitation is taking place. So, if you look into this particular diagram, so here is the prism, you have a thin metallic layer and then you have air on the other side. So, this is the incident beam. Typically, as we have seen that only TM excitation is allowed. So, you can think of a TM beam to be incident, that is total internal reflection. Some energy will be there, but along the metal prism interface, it will be evanescent wave. So, that will die off very quickly, okay, that will not be able to propagate. But then some part can actually tunnel through and then excite surface plasmon on the metal air interface, and that can propagate along the surface of the metal for certain distance. Okay. So, in short, the SPPs are excited, they can be excited using phase matching condition, where the condition will be beta equals k square root of epsilon sin theta. So, this is the condition with which you are able to generate SPP. Now, there is another configuration in prism coupling which is called auto configuration. Okay. Now, in this case there is a gap between the prism and the metal film. So, there is basically a thin air gap. Okay. Now, in such case what happens, again total internal reflection takes place, and then the SPP excitation on the metal air interface takes place via tunneling to the air metal interface. So, from here to here the excitation has to tunnel, and then you can excite the surface plasmon on the metal air interface. Now, in which case this will be useful? This kind of configuration is useful when no direct contact with the metal surface is allowed. Okay. Something like, say you want to study the surface quality of a particular metal, in that case you will not be able to touch the metal surface. So, in this case auto configuration will be useful because the prism is placed at a particular gap from the surface. Fine. So, with that we can think of another method of SPP generation besides prism coupling. So, that is grating coupling. Now, the problem remains same here, because that there is a phase mismatch between the incoming photons and the surface plasmons which are supposed to generate. So, how do you match the momentum or the phase? Okay. So, here you can see that the in plane moment, which is k parallel, is nothing but k sin theta, right. If you take this as your theta, so this component is nothing but k sin theta, right, and beta is the propagation constant of the surface plasmons. So, what you can do, you can actually generate a grating, okay, of groups or small holes with lattice spacing of a. So, if you do that, what happens, you can actually get, because of this one dimensional grating of groups, phase matching can take place by this particular condition being satisfied, that beta will be k sin theta plus minus nu g. What is nu? That is integer 1, 2, 3, and g is basically the reciprocal vector of this particular grating, which is 2 pi by a. So, with those possible cases, okay, so you will be able to generate or you will be able to transfer energy between photons and plasmons. Okay. If you try to think intuitively what will happen, because of this grating, when light falls on it, okay, it will allow you to excite all different modes, not only the fundamental mode, first order mode, second order mode, third order mode, and all the higher order modes. So, there is a possibility that with one of these modes, the beta, the propagation constant of plasmons, will have a phase match, and that is how you will be able to excite. And here also it is shown with a notation, as you can see, more field is towards the dielectric side and there is less field penetration into the metal side. So, this is an example of grating coupling for generation of SPPs. Now, let us look into some applications of SPP. First, sub-wavelength optics. Okay. Now, controlling light on scales much smaller than the light wavelength can be achieved by excitation of SPPs. Now, that is the reason why people have moved to Plasmonics, that it allows us to break the fundamental diffraction limit of light and allow you to get much smaller wavelength at a particular given frequency. So, if you go back and see the dispersion relation, everything lies here in the dispersion relation. I will go to this one, the first one I have shown. Yeah. So, here you see that the dispersion relation in air or any other dielectric photonics, it is linear. So, omega equals C k, or you can say omega equals C by n k, where n is the refractive index of the dielectric medium, right. But in case of SPPs, you have seen that omega is basically a non-linear function like this. So, that allows you to actually have for one particular frequency, you can see you can have very large wave factor, that is also possible. So, say you choose this particular frequency, for optics this will be the wave vector, okay, or the k value, but for the plasmon this is the wave vector value. So, you can see that the wave vector is very, very large, and k and lambda, they are inversely proportional. So, when you are able to get a large wave vector, it means you are able to get very small lambda, and that allows you to confine and guide light in a wavelength scale which is much smaller than the photon's wavelength, okay. Or you can say you can actually go to X-ray scale while you are still in the optical frequency. So, that is the beauty of plasmonics, okay. I am going back to the slide where we left. Yeah. So, SPPs, they have potential application in sub-wavelength optics. Obviously, you can use them for waveguiding, they can be used as source, detector, modulator, sensor and so on. We will also see each of these applications here, just some schematics, we will see them in details in the next slides. So, first one is a metal wire SPP waveguide, okay. So, chemically prepared silver nanowires with a well developed crystal and surface structure can sustain non-radiating surface plasmon modes with wavelengths shortened to about half the value of the exciting light, okay. So, that way you are able to guide light in a scale which is much smaller than the wavelength. So, that is actually sub wavelength. Now, part of the incident laser is basically scattered into surface plasmon mode, which propagates towards the distal end of the wire. So, you can actually see in this figure that I is the input, D is the distal end. So, you are first shining a laser excitation to the input end, and then you allow light to get converted into plasmon and propagate to the distal end. So, it is something like this, you are having the excitation here and it travels through this particular nanowire, and towards the end it again gets back to light, and which is also visible, okay. So, this actually shows the scanning near field optical microscopy image and shows how exactly the plasmon is propagating in this nanowire. So, there are other types of waveguides also possible. So, some important ones are like metal groove waveguides. So, what is these groove waveguides? They actually allow photonic and plasmonic coupling. So, integrated waveguide coupling was implemented for excitation of plasmonic modes in tapered grooves. So, tapered grooves are like this V shaped, okay. So, they actually allow plasmonic mode excitation via the photonic modes of silicon ridge waveguide. So, silicon ridge waveguide, you understand that they are actually much larger in dimension, but then you can actually make metallic groove waveguides and convert photonic modes to plasmonic modes, and then allow them to propagate or carry that information in a sub wavelength regime. So, for the metal groove waveguide, there exists a fundamental mode and a higher order mode, which are also called channel plasmon polaritons or CPP. So, some example you can see here that there is a grating, on top of that laser light. So, this is the optical signal that you are taking. you have a grating coupler that converts your light into surface plasmons, right. And once it is getting coupled, you can actually, so you can actually get plasmons over here, but then you actually put a silicon waveguide from this one to the V groove. So this is how the V groove will look like. Okay. So there will be very strong confinement of electric field towards the narrow end of the groove, and this allows you to have photonic and plasmonic coupling, right. So first you have this laser light falling on the grating, then you have the silica ridge waveguide that, or sorry, silicon ridge waveguide that actually carries the photonic modes. Okay. So to couple to this photonic mode also you need grating. Okay. So this is not converting directly to plasmons, but then from here you are actually exciting channel plasmon modes. So this is the coupling that happens between the photonic and plasmonic modes. So the resonant guided wave network can be realized using plasmonic CPP V groove waveguides. They also allow design of ultra compact power splitters and logic devices, because you can actually do this kind of splitting and manipulation in a much smaller scale as compared to the photonic integrated circuits. Okay. So here is an example of plasmonic Y splitter. So this is the ACM image of the Y splitter. You can see these are basically the grooves. So the depth is d, the angle of the groove is theta. This is the topographical image, that is from the top how it looks like. So this is the Y splitter, and this is the near field optical S-norm image that shows you how the splitting is taking place. The similar thing is also shown for plasmonic Mach-Zehnder interferometer. You might have heard of Mach-Zehnder interferometer as modulators in optics. So you can actually have plasmonic Mach-Zehnder interferometer as well using this kind of groove structure. Okay. So the energy can be confined to different positions in the groove depending on the modes and wavelengths. So depending on the modes and the wavelength, you may actually confine energy at different position of the groove. So that is why the groove structure is also very interesting. The modes and propagation distance can be tuned through the taper angle. So that actually allows you this taper angle is the theta. So that will also decide what will be the mode that is being supported or propagating and what is the propagation distance. Okay. So now let us look into another one which is called double strip waveguide. So for the double strip waveguide, the basic mode is similar to the low energy mode of an MIM structure, that is metal insulator metal kind of structure, and the surface charges are opposite on two sides. So this is how the structure looks like. It is a double strip waveguide. There is an edge or tapering towards the end, and if you see the surface charges, they are basically opposite when they are oscillating along the propagation direction. So this wedge waveguide is highly similar to the groove structure, and you see the energy is confined in the edge. Here also you can see this is the near field image of the intensity pattern. Okay, and you see towards this particular groove you have the highest energy concentration. So the tapering results in the compression of the electromagnetic energy that is being carried by the surface wave. So this way you are able to localize energy at a particular point, or you can take out energy from particular points. So that way you are able to guide, manipulate the optical field or optical energy in sub-wavelength dimension. Another application is of plasmonic laser. So a light source at the nanometer scale is very important to build a plasmonic circuit. So if you have all the components of your circuit in nanometer scale, you also want your light source to be in the nanometer scale, right. So Outon and all, they have presented a SPP laser at the deep sub-wavelength scale in 2009, and they optically pumped the SPP laser elements at a wavelength of 405 nanometer, and they found emission at 489 nanometer. So, typically this was the structure of the plasmonic laser. So, it consists of a cadmium sulphide semiconductor nanowire, okay, on top of a silver substrate with a magnesium fluoride spacer. So, there is a thin layer on top of the silver one, and this is the structure. So, they used 405 nanometer as pump, and they were able to excite emission coming out at 489 nanometer. We will not go into too much of details of how this lasing action happens here, but this is very similar to the photonic lasers, okay, the pumping and all the concepts are also very similar. Okay. So, here is an explanation of how it works. So, when you look for plasmonic laser, there is another effect that helps you to tune the laser wavelength, that is called surface plasmon polariton SPP enhanced Bernstein-Moss effect, BM effect. Now, what is this effect? So, Bernstein-Moss effect is basically a phenomena in which the apparent band gap that you see in a semiconductor is basically increased as the absorption edge is pushed higher, okay, because some states which are lower, okay, they are basically being populated. So, if you want to jump from your valence band to conduction band, these states are already filled up. So, you cannot actually go there. So, you have to go to higher energy level in the conduction band, and this effect itself is called, this shift that you see delta BM is basically the BM effect, and that takes place when you use high pump fluence. Okay. So, this is under normal or low pump fluence, okay. There is no BM effect, Bernstein-Moss effect. In this case, okay, you are actually using high pump fluence and you are able to see this particular effect, okay. But when you actually excite, you set up this particular geometry. So, here it is only cadmium sulphide nanowire on top of silica. So, there is no possibility of exciting surface plasmons, but when you bring silver film and then there is a thin layer, dielectric layer, okay, you are able to excite surface plasmons, and those surface plasmons will actually enhance this particular effect, and it is called SPP enhanced BM effect. So, that allows you to see more change in the absorption level. So, obviously, the emission laser wavelength will also be different or changed. So, the excitation, emission intensities and recombination rates of the semiconductor can be tuned, and thus the emission laser wavelength can also be tuned. And this particular effect is the apparent blue shift of the optical gap of an semiconductor, and it comes from the state filling close to the conduction band. So, this is the region that the states close to the conduction band valley are already filled up, and that is why you have to move to the upper energy levels, and that gives you that particular tuning. Now, here is another plasmonic laser. It is basically indium gallium nitride based plasmonic laser in a MOS metal oxide semiconductor configuration. As you can see here, this white shiny piece is basically silver film on silicon. So, this yellow one is silicon, and then you have a 5 nanometer spacer which is aluminum oxide, alumina Al2O3. On top of that, you have the semiconductor nanowire, okay, or nanorod. So, what is happening? It is basically metal oxide semiconductor kind of arrangement, and you are able to see that this indium gallium nitride or gallium nitride nanorod plasmonic lasers are able to give all different colors, Okay. So, all color single mode lasing images, as you can see here, it's starting from 474, that is kind of blue, and then 627, that is red. So, all this can be observed from single nanorod with emission with line width of around 4 nanometers. So, that is very good. So, what you have to change? You have to actually change the size of the nanorod, and that will allow you to get different colors out of it. You can also make electro-optic modulator based on this SPP waveguides. So, this was the structure that we have briefly seen before. So, here it shows a high speed SPP phase modulator. So, you can see continuous wave coming in, then you have gold plates here, there is a kind of slot in between, okay, and that is the plasmonic waveguide, which is filled with some kind of non-linear electro-optic polymer. Now, when you apply voltage in the sense of 101101, this kind of voltage, you will be able to do some shift, okay, in the material property of that polymer, okay, and that will allow you to introduce some kind of phase modulation. So, 101101, this is how the output is actually getting phase modulated. Now, what happens here? It will actually use the Pockels effect of this nonlinear electro-optic polymer. Now, when I say Pockels effect, it is basically the Pockels electro-optic effect, and it is also known as the linear electro-optic effect. It means the Pockels effect is a directionally dependent linear variation in the refractive index of a optical medium in the response of an applied electric field, right. So, when you apply this electric field across this material, which is an electro-optic polymer, there will be certain changes in the refractive index property, and that will allow you to get this kind of modulation done. So, here also this V groove kind of thing, it is not complete V, it is like this, okay, slot is there in between. So, this is the fabricated structure seen from the scanning electron microscopy image, SEM image. So, if you look into this part and you see the zoomed in, so this is how it looks like, okay. So, there is a taper, okay, and in this region that electro-optic polymer is located. So, you are able to obtain a high operation speed like 40 Gbps, and this particular modulator is thermally stable up to 85 degrees centigrade. So, that is quite high. So, you can understand that this particular device or modulator is very stable. You can also think of plasmonic detectors. So, Falk and al. In this particular paper in 2009, they have reported an electrical SPP detection technique based on near field coupling between the guided plasmons and a nanowire field effect transistor. So, first you have a silver nanowire, so that is bringing your plasmons, and then here you have is nanowire, so it is a germanium nanowire field effect transistor. So, these are the bias voltage, gate voltage and everything connected. Okay. So, whenever there is propagating SPP modes, they in this silver nanowire, they get coupled to this germanium nanowire detector, and they excite electron hole pair, and this electron holes they propagate, and there is a current in the circuit which is measured. Okay. So, this device is in nanoscale, and it demonstrates the possibility of future on chip optoelectronic devices. So, you can see here, this is the setup or schematic in which this plasmon detection will work, and this is the SEM photograph of the device. Okay. And always remember that the ratio of the detected charges to the number of SPPs reaching this particular silver germanium junction is defined as plasmon to charge conversion efficiency. So, higher this efficiency, better will be this detector, right, plasmonic detector. There are other types of detector as well. So, that was proposed by Goekman et al. In this particular paper in 2011. They proposed an on-chip silicon surface plus bond Schottky detector. So, Schottky means it is a metal semiconductor junction is there. So, you can see this kind of groove waveguide structure. There is gold metal, there is aluminum connectors. So, here is aluminum contact. This is the ACM image. You can see the gold contact here. You have a SPP waveguide. So, this is how photonic in and photonic output. Okay. So, this is basically silicon on insulator and this is buried oxide, this is the oxide layers. So, this is how the structure looks like for this particular detection. Now, the advantage of the detector is that it can be easily integrated with other components with traditional fabrication technique, because they are using all the conventional materials, and they actually achieved a efficiency of 0.25 and 13.3 microampere per watt at the wavelength of 1550 and 1310. These are the telecom wavelengths, okay, and they were able to get this to particular efficiency. Okay. So, this is how you can also detect surface plus bonds. Surface plus bonds are also very important for sensing applications. So, this is one particular prism coupling arrangement that you have already seen before. So, using the surface functionalization, agent binding or agent specific binding can be achieved, and that will change the refractive index of the metal surface superstrate, and that actually changes the dispersion relation of the propagating surface plus bond. So, this is basically the funda behind surface plus bond based sensing. So, here you can see you have got the prism, then you have index mesh substrate, okay. Then you have this dielectric buffer layer in between. So, this is the metal layer where surface plus bonds will be excited, and on top you have got a superstrate, okay. So, that is basically some kind of functionalization to do some agent specific binding. Now, the binding event can then be monitored by studying the changing phase matching conditions, which is achievable by either changing the wavelength or the incident angle, right. So, these are called wavelength or angular interrogation. So, you change the wavelength of the incident photon or you change this particular angle, okay, you will be able to excite different surface plus bonds. So, historically for sensing application, both prism coupling and grating coupling techniques have been preferred for SPP excitation via light beams. So, this is an example of such kind of arrangement. So, what you will do, you can actually send light from here, and here you will have a detector. So, depending on the analyte, and if they are able to do some agent specific binding, there will be a change in the refractive index here, and that changes the dispersion relation of the plus bonds. So, plus bonds will then get excited at different wavelengths. So, that is what is also seen here, that when n is 1.333, you get the dip here. Dip in the reflected spectrum means the energy is basically getting transferred to some other form, okay. It is not coming back to you, it means it is getting transferred. So, where it gets transferred, it actually gets converted into plus bonds. So, this is the case, but when the refractive index of this analyte or this medium changes to 1.342, okay, the wavelength shifts to this particular value. So, you can see you can actually detect them very easily. So, that is a popular application of SPP. So, here also it's been used or it's shown in a much better configured manner. So, you look at the circles here, they are basically the analyte, and the Y entities that you see, these are basically the ligands. So, this is again the same kind of arrangement, just shown in a top down manner. So, you can have a microfluidic channel like this, okay, and you can let this analytes move, and whenever they get binded here, this is basically the gold film which has got this surface sensor. So, as there will be more binding, there will be change in the refractive index in this region, that will change the wavelength of that plasmon excitation, and that can be detected. So, usually you use helium neon laser as light source and CCD or charge coupled display device, okay, or charge coupled device CCD as that detector. There can be other type of refractive index sensor as well using SPPs. So, here is a surface plasmon polariton fiber sensor with a fiber Bragg grating imprinted on the fiber core for SPP excitation. So, this is a typical fiber, as you can see, this is the core, this is the cladding, and this is the substrate, that is the surrounding media NS. So, there is a short grating in this particular it is called short period fiber Bragg grating, as you see, of length L. So, what it will do? It will particularly reflect a specific wavelength. So, that wavelength, when it comes back, okay, it can leak out to this particular cladding, and there is, if there are metal deposited on top of this cladding, there is a metal dielectric interface, and that light can excite surface plasmons which will be propagating along this metal dielectric interface. How does it help? So, depending on the refractive index of the surrounding medium, okay, the wavelength of this excitation will change, and that can be measured here, as you see. So, when NS is changing, okay, you are able to see the difference in wavelength. So, you can actually make refractive index based sensor, because whenever there is a change in refractive index, the wavelength of light that is getting coupled to the surface plasmon is also changing. So, that way you will be able to measure the change in the refractive index, and people are able to do really high sensitivity like sensing of refractive index using SPP sensors. Even change in refractive index of the order of 10 to the power minus 7 was also possible using this kind of sensing. So, you can understand how sensitive this particular mechanism of SPP excitation is to the surrounding medium. Okay. So, with that we will stop here today, and in the next lecture we will take you to another aspect of surface plasmons, that is the localized surface plasmons. Okay. So, if you have got any queries on SPPs, on their applications, you can drop an email to me at this particular email address. Make sure you mention MOOC on the subject line. Thank you.